So we're at the top of the hour. I think we'll go ahead and just start with the introduction and give Rajesh a little bit of time to get his slides set up. So thank you all for joining us. This is the concurrent session C for Gateways 2020 with the theme of managing data research products effectively. We have 3 presentations. Each will be 10 to 12 minutes, followed by Q&A for about 3 minutes. We will have 15 minutes at the end of the hour to do a wrap-up discussion, so I hope you all will stay tuned for that and give maybe some broader questions for our authors to answer. But starting up first, we have GeoEDF, a plug-and-play workflow framework for Earth science research by Rajesh Kalyanam. Rajesh, would you like to start?
Yeah, sure. Thanks, Claire. And I'm sharing my screen. You can see it now, right? Awesome, thanks. All right, well, welcome everyone. I wanted to start this demo of GeoEDF with a quick preview of GeoEDF in action and then maybe move on to some technical details. So here is a really simple illustration of a workflow that's pretty common in hydrology. So it's actually depicting a pre-processing workflow where satellite data that's stored in a NASA DAC or a distributed active archive center, which is their distributed repositories, needs to be processed in the context of a watershed and then use the resulting data for a hydrologic model. So the data in the NASA DAC is actually HDF files, which if you're familiar with geospatial data, it's actually a gridded raster format. The watershed itself is actually a shape file, which is a vector file that contains a bunch of polygons showing the different subbasins. And so the goal here is to essentially take a weighted average of the gridded values in the HDF file for maybe one of the sensor values. In this case, we're looking at the leaf area index, which is related to vegetation cover, and then get a weighted average for each of the subbasins so that you can then use it in your hydrologic model. So if this was a savvy researcher, then you would expect that they might maybe automate some of these pieces. So they would probably write some code that downloads data from this NASA DAC, maybe use some GIS libraries to do the masking and aggregation operation to get the weighted averages and then use that in their model. If the researcher wasn't as savvy or if they were in a hurry, then maybe they might just go to the NASA DAC's webpage, download the data from there, use a desktop GIS tool like QGIS or something, do the weighted average that way, and then use it in their hydrologic model. So what does GeoEDF let you do? So in GeoEDF, you can actually write a workflow that looks something like this. I will get into these individual pieces in a few minutes, but the essential message here is that you can write a really simple, high-level sort of declarative workflow. In YAML syntax, you point it to the endpoint where the data is located. You can use things like wildcards and other options to query for data. You provide your authentication details to this repository as the first step, and then the second step, you point to the shapefile for your watershed that you want to model. Put in a reference to your data that you've downloaded in the first step. So you write this really simple high-level workflow file, and then you use GeoEDF to essentially execute it. So let me just reset my Zoom. So if you go all the way down here, it's essentially just a 3-step process. GeoEDF is at the bare bones just a Python library, so you can import the library, instantiate your workflow. It's going to prompt you for your authentication password because you don't want to store that in plain text in your workflow file. Once that's done, then you can have it execute, and this takes a while. So while this is running, let's talk more about what GeoEDF actually is. So, all right. So as you've seen, a lot of the workflows in the geosciences are usually just data wrangling workflows. So you often have to use data that's maybe collected by satellites or a survey from like USGS or something. So most of these data sets are collected by large organizations and then managed in their own data repositories. And so a majority of your time is usually just spent wrangling data before you can use it in your research. And we want to free researchers from this responsibility and sort of help them maybe focus more on their science than in the data wrangling, which is often the boring parts of your job. And this also has a pretty significant relationship to reproducibility, because as you've seen, if you have a researcher who is doing this on their desktop, then that's pretty hard to translate and share with other people. And so even if you have a science gateway, your researcher might either just be using it when they need to get access to HPC resources, or they might do all of their processing offline, then just put up the final results on your science gateway. And that's not really a very sustainable approach to fair science. So the ideal situation is it's what's depicted on the right, and that's what we hope to achieve. So the goal is that your researcher can come to a science gateway, define a high-level workflow in some powerful but user-friendly language, ask the framework to execute it, and then now that you've got a gateway which has all of these data publication and annotation tools, then you can essentially leverage all of that to publish both the data and your workflow and keep track of provenance. So that's our eventual goal. And so GeoEDF really is designed to sort of help you bridge the gap between this current state of the art that's represented on the left and then what we hope to achieve on the right. So this is a 5-year project that's funded by the NSF CSSI program. We just completed our 2nd year. It's led by a pretty large group of multidisciplinary researchers. Our PI is Carol Song, my boss, who comes from cyber infrastructure. We've got several science PIs who represent different earth science domains who provide most of the initial use cases for this project. So GeoEDF really has 3 key design principles, and this is what we use to sort of operate and sort of achieve the goals that I laid out in the beginning. So our first goal is to take a complex geospatial workflow and then try and break it down into its constituent data access and processing steps. So once you've identified these steps, then our next goal is to then build these abstract but reusable building blocks that can help achieve these individual pieces, so individual data access or processing operations. And so once you've got those reusable building blocks, then essentially connect them to cyber infrastructure frameworks that you already have, so that you can then help promote fair science principles by letting your workflow run completely in a CI or a science gateway environment. So GeoEDF has 3 main components. There's data connectors, which implement these access operations, data processors, which implement the processing operations, and then a workflow composer that allows you to connect connectors and processors together into reproducible and reusable workflows that can run in a variety of computer environments. But operationally, these are just Python classes. So connectors and processors are just Python classes that implement a standard class interface. The workflow composer has 2 pieces that you just saw. So there's the syntax itself that tells you how you can compose these connectors and processors together into a workflow, and we use YAML for that. And there is a workflow engine that's essentially a Python library that's built on top of Pegasus, which is a workflow management system that allows you to essentially define this YAML workflow, and then the engine takes the YAML workflow and then figures out how to execute the corresponding connectors and processors in whichever computer environment we've set up for that. So let's, with that sort of quick overview of GeoEDF, let's go back to our workflow. You can see it's running here, but then if you sort of apply the design principles that I just talked about for this workflow, then you can see the first step essentially was where you wanted to get maybe HDF data from a NASA DAC, and then use that and then process that along with a shapefile. And so there's really two pieces to this workflow. So you have a connector that's doing the task of essentially getting the data from the NASA DAC, and then you have a processor that's really generic. So all it does is it takes an HDF file, it takes a shapefile that has polygons in it, and it calculates weighted averages for each of the polygons. So it's not really a domain-specific processor. It's a more generic, reusable processor that can be applied across different domains. So then if you go back to look at the workflow itself, that's really just a collection of instances of these Python classes that I talked about before. So NASA input, which is our connector, is a Python class. These are the class attributes, and all you're doing here is just representing an instance of that. So you're providing the URL and your authentication details. The HDF EOS shapefile mask is a processor. Again, that's a Python class which has 3 class attributes. One is the HDF file that you want to process. The second is a shapefile. And then finally, there is the list of data sets from the HDF file that you want to use. You can have any number of data sets here. So why and how would you create a new connector or processor. So our goal here really is to sort of solve all of these pain points for our researchers. And so we will build these initial set of connectors and processors based on the use cases that I mentioned before. But there's also the notion that we don't want this to be a project where we are building a huge repository of things that people may not really need. And so this is really intended to be a sort of community-driven project. So once we have a few examples of connectors and processors, then we hope that our researchers would then use that template to build their own. And since they are Python classes, they are pretty straightforward. So let's, I have some trouble moving this thing here. So let's talk about this workflow a bit more. So, so the end of this workflow, you essentially get a new shapefile here that has a new field which has the weighted averages filled in. But then if you're working in Python, then that's not really something that you can visualize very easily if you're familiar with the different Python libraries. And so we may want to convert it into a format that's maybe a bit more useful. So you can, for example, write a processor that takes a shapefile, converts it into GeoJSON. And this, again, is a really simple Python package. All you need to do when you're writing a connector or processor is ensure that you've used the right package structure and implemented the right methods. In this case, for a processor, you need to implement a process method. And then that's all you need to do. And I should mention that connectors and processors are actually encapsulated and packaged as singularity containers here. And the reason we do that is because that makes it easier for you to execute it across different environments without having to worry about the software dependencies. And so we have a helpful script here that allows you to build an image. And then once you have those singularity images, then now you can use this to write a new workflow, which has 3 steps. So after you're done with the first 2 steps, you can tag on your shapefile to GeoJSON processor at the end as a 3rd step that takes the input from the 2nd step and then creates a GeoJSON. In the interest of time, I won't run that workflow. The other one's running and it's taking a while. So you can do the same thing here. And then once that's done, I'm just going to skip right to the end, assume that that workflow is done and I have it run before. But then now, since I have a GeoJSON, I can visualize it pretty easily with a Python mapping library like Folium. And so there you go. That's essentially the final output. So skipping really quickly back to my slides. So yeah, so as you might have gathered, I was using a Jupyter notebook there to demonstrate all of this. And really my intent there was to show that this is intended to be a package that can be installed across a variety of CI environments. So it doesn't have to be a specific science gateway or a particular framework. But then the production setup would look something like this. And this is something that we're still working on. So on the top here, you have your contribution process for connectors and processors. We use GitHub for that, just regular open source pull requests and feature branches. And we have a CI/CD pipeline that essentially just builds the singularity containers when you, as soon as you create an update for your particular connector or processor or add a new one. And we have a singularity registry that hosts all of them. The piece here at the bottom is something that we're still working on. We are actually working on integrating GeoEDF with Hub 0-based Science Gateway, my GeoHub, which is our production gateway. So that's still work in progress, and we hope to have it done soon. So we are shooting for December to have that done on my GeoHub. But the one that I was demoing today, that's actually just a Docker container that you can download from this link here, and you can run it on your local laptop and build Singularity containers right there in that particular Jupyter environment, and then write your own workflows. And we've actually got our colleague Jack Smith, who's been using that to develop his own connectors and processors. So with that, I will stop there and put up the slide with all the links and contact information. Thanks.
Thank you very much, Rajesh. We have our first question from Chun Han. So this is, how can you manage large data case to load the data?
Okay, so so the workflow itself, the way it's and our main use case is that you're pulling in data from large remote repositories. So there's nothing really that's coming down to your Science Gateway or your CI. So when the workflow runs, it's running on a remote resource. It might be running on a cluster. And if your first step is a connector that's pulling down the data, then that pulls it down to the cluster and then it works there. So the only thing that's transferred back is the final results. And so there's no intermediate data that's transferred back. None of the data that's pulled in any of the steps is transferred back to your gateway. So, so as long as the connector can pull in data from the remote repository, use it in the cluster, then it'll work. We do intend to support several protocols. So right now we do things like HTTP and FTP. We are planning to do OpenDAP, but then if you maybe had a large data set and you wanted to use Globus, then we can write a connector that uses Globus to pull in that data into wherever the compute is.
Perfect. Well, thank you very much. And I think there is one more question in chat, but maybe you can answer that, or we can talk about it at the end of the session. But really appreciate your time today.
Sure.
So next up, we have